The next problem, it says that an object is moving with an initial velocity v naught, undergoes a constant acceleration for time t. Find the final velocity. All right, so to find the final velocity, we're going to use the equation acceleration equals change in velocity over time. We're going to rearrange this equation to solve for final velocity. Now, take that time to the other side to get change in velocity is going to be equal to acceleration times time. If you remember, change in velocity is final velocity minus the initial velocity. So when you add the initial velocity to the other side, that gives you your final velocity is going to be equal to the initial velocity plus acceleration times time. So if we look at this equation, we can actually see what we're calculating. Notice here that we have final velocity minus initial velocity equals acceleration times time. So if we look at an acceleration versus time graph, especially if it's a constant acceleration, an acceleration versus time graph, the change in velocity equals this area. So the base and the height would be acceleration times time. So that's where we get that the area of an acceleration versus time graph will actually give us change in velocity. All right, object A and B are both, they start at rest, both accelerate with the same rate. However, object B accelerates for twice the time as object A. For the final speed of B, compare that to the final speed of A. So what happens when you go for twice the amount of time? What happens to the final speed? Well, if you look at the velocity, the final velocity equation that we came up with twice the time, we have twice the final velocity, because the final velocity is going to be equal to acceleration times time. So 2 times the time is going to give me 2 times the velocity. So in this equation, we have displacement that's going to be equal to the initial velocity times time plus acceleration times time squared over 2. Now this equation we haven't really talked about yet, but I want to show you where this equation comes from. If we look at a velocity versus time graph, all right, and we start with some initial velocity, if we take the area under this graph, that'll actually give us this equation right here. So you can figure out the displacement when you have a constant acceleration by taking the area of a velocity versus time graph. Now this area down here, that represents the initial velocity times time. That's this first part right here. And then this area up here is a triangle. And if you notice, the height is going to be a change in velocity. And if you multiply change in velocity and divide by time, then that'll give you acceleration. So if we take that change in velocity, divide by time, and then multiply by time, the change in velocity over time gives me acceleration. And then we get the time. And notice there's another time because that's the base. So we get time squared. And then since we're dealing with a triangle here, that's where we get the 1/2. So each part of this actually added together gives me the total change, the total area where they've got the initial velocity times time and the acceleration times time squared divided by 2. Those added together gives me the total displacement. All right, object A and B both start from rest, both accelerate with the same rate. However, B accelerates for twice the time as A. So how does the distance traveled, how does that compare for each one? Well, if you look at the equation for displacement equals 1/2 times acceleration times time squared plus the initial velocity times time. Both of them start from rest. So with twice the time, that twice times the time is going to be squared. So that means it's going to be 4 times. All right. So with this equation right here, with no initial velocity, I got acceleration times time squared divided by 2. So 2 times the time, that 2 times is going to be squared. So it's going to be 4 times as far. So here are our equations. We got our initial velocity is going to be equal to the final velocity equals initial velocity plus acceleration times time. And then we got displacement is going to be equal to initial velocity times time plus acceleration times time squared divided by 2. Now, if you combine these two equations, you can do so in a format that actually tells you something a little bit interesting here. Here's another equation that we have. The acceleration equals change in velocity over time. That's actually this equation rearranged. And if you take your displacement equation, that equals initial velocity times time, and you plug this in, you can actually see that your time is going to cancel here. And then you get minus the initial velocity over 2, and then you got initial velocity times time. And that'll actually combine to give you this equation right here, the total displacement, as long as you have a constant acceleration. Now, we have to clarify that this equation only works when you have a constant acceleration, but you can actually add your final velocity and your initial velocity, divide by 2. So that kind of gives you an average velocity. Now, again, only with an average, when you have a constant acceleration can you do this. But the final velocity minus the initial velocity divided by 2, so you get an average velocity multiplied by time, and then that gives you displacement. Now, when you combine these two equations in a different way, when you plug in for time, then what you can do is you basically get this equation, which looks like a mess, but when you actually solve it out, you get this equation where the final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. So this next question says, when the velocity of an object is 0, must its acceleration also be 0? Now, for a velocity to be 0, it doesn't actually have to have 0 acceleration. There is an instance, part A right here. It says, no, an object that's thrown upward has 0 velocity when it gets to its highest point. So an object that hits a velocity of 0, that just means at that moment, that instant, it's not moving, but it can still be accelerating during that time. Just it changes direction whenever it accelerates and has a velocity or has an acceleration while it stops. This question says, when the object is released from rest and falls to an absence of air resistance, which of the following is true about it concerning its motion? So with no air resistance, gravity is going to be pulling it down and its acceleration is going to be constant. Velocity can't be constant because as it's falling, gravity is pulling down on it. All right, here it says 2 cars are traveling with a straight line in the same direction. The lead car is 25 meters per second. The other car is 30 meters per second. At the moment that the cars are 40 meters apart, the lead driver applies the brakes, causing his car to have an acceleration of negative 2.0 meters per second squared. So the question is, how long does it take for the lead car to stop? So the one that's going 25 meters per second. All right, so we're trying to find the time, and we have the initial velocity, the final velocity, and acceleration. So what this means is we're finding time with respect to initial velocity, final velocity, and acceleration. So we list that information that we know. The initial velocity is 25 meters per second for the lead car. It's going to stop, so the final velocity is 0. The acceleration is negative 2 meters per second squared. So we've got our kinematic equations. Knowing that we have the initial velocity, the final velocity, and acceleration, we're looking for time. Then we're going to use this first equation right here. We'll go ahead and plug in our information. The final velocity, well, we're going to rearrange for time so that we take the initial velocity the other side, final velocity minus the initial velocity, and we divide by the acceleration to isolate our time. So 0 minus 25 divided by a negative 2. That gives us negative 25 over negative 2, and we get 12.5 seconds for the time. The second part, it says, how far does the lead car travel during this acceleration? So while he's traveling, he has an acceleration, he has an initial velocity. So we're trying to find that displacement, and we have all these pieces of information. Now, personally, I don't like using time just because we calculated it. So we can use that because we technically know what it is, but calculating an answer and then using it again means you're going to get some rounding error. So this example, we use our kinematic equations. We can use this bottom equation where displacement is going to be equal to the final velocity plus the initial velocity divided by 2, multiply that by time, and then we get our displacement is going to be equal to 156 meters. Now, because we have multiple equations, we can actually solve this in multiple ways. So if we use this middle equation right here, where displacement is going to be equal to the initial velocity times time plus 1/2 times acceleration times time squared, we plug in our information, 25 times 12.5, and then we plug in the acceleration, the time, we get 156 meters again. Now, the way I would actually do this is because we calculated time, I would actually use the information that's given to us at the beginning. That's the final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. So then we solve for our displacement. We subtract the final velocity squared minus the initial velocity squared. Then we divide by that 2 acceleration. We get 156 meters. Now, technically, you get the same answer either way, but it's a little bit better because you don't get the rounding error that kind of goes through the problem. The next question, it says, assuming the chasing car brakes at the same time as the lead car. So the chasing car, the one that's moving at 30 meters per second, starts braking. So what's the minimum negative acceleration so it does not hit the lead car? All right, so we're trying to find that acceleration where we know the initial velocity, which is 30 meters per second. We know the final velocity is going to be 0, and the displacement is going to be 196 meters. Now, why is it 196? Because the lead car took 156 meters to stop, and then the second car is 40 meters behind it. So the second car has an additional 40 meters to travel, so it's a total of 196 meters for the second car. So using our kinematic equations, we know the initial velocity, we know the final velocity, we know the displacement. We use this to find the acceleration. We can use this equation right here, final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. We go ahead and plug in our numbers, and we get that our acceleration is going to be equal to 0 squared minus 30 squared divided by 2 divided by 196, and we get negative 2.29 meters per second squared. The next part of the question says, how long does it take for the chasing car to stop? So what's the amount of time? All right, so we know the acceleration and we know the displacement, so we can use those in order to figure out the time. So we got the initial velocity, we got the final velocity, we got displacement, we got acceleration. So which equation we're going to use to find time? I would say the easiest one would probably be the best. So we got initial velocity is going to be equal, or final velocity equals initial velocity plus acceleration times time. We go ahead and solve for our time. So change in velocity divided by acceleration, so 0 minus 30 divided by negative 2.29, and that's going to give us our time is going to be 13.1 seconds. All right, in this problem it says a drag racer starts her car from rest and accelerates at 10 meters per second squared for a distance of 400 meters, which is about a quarter of a mile. So how long did it take for the car to travel this distance? All right, so knowing the initial information, we have the initial velocity, we have the acceleration, and we have the displacement. So that's what we know, and we're trying to find the time, so we need an equation with time with respect to those variables. All right, so looking at our kinematic equations, the one that we have for time, initial velocity, displacement, and acceleration is going to be this equation right here. Displacement is going to be equal to the initial velocity times time, plus the acceleration times time squared divided by 2. So we need to solve for time. Now the initial velocity is 0, so that part goes away, but then we multiply the other side by 2, so we get 2 times displacement, divided by acceleration, and then to get time we have to square root both sides. So we go ahead and plug in our numbers. We find that our time is going to be equal to 8.94 seconds. In part B, it says, what is the speed of the car at the end of the run? So how fast is it going at the end? So we know the initial velocity. We now know the displacement, acceleration, and the time. So knowing all of that, which kinematic equation we're going to use, probably the one that's a little bit easiest to use. So the final velocity equals the initial velocity plus acceleration times time. We go ahead and plug in the numbers we know, and we get that our final velocity is going to be equal to 89.4 meters per second. In this question, it says a ball is thrown vertically upward with a speed of 25 meters per second. How high does it rise? All right, so there's not a lot of information given to us other than the fact that it's moving at 25 meters per second. Now, since it's thrown upward into the air, on Earth, the acceleration due to gravity is negative 9.8 meters per second squared. As long as we don't include air resistance, the acceleration due to gravity is going to be negative 9.8 meters per second squared. Now, what's interesting about this is how high does it go? At the highest point, the final velocity will be 0 because as it goes up, it's going to eventually stop. So we got the initial velocity, we got the final velocity, and we got the acceleration. So which equation we're going to use to find the displacement is going to be this one right here. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Solve for your displacement, so we take the initial velocity squared to the other side, and then divide by 2 times acceleration, plug in your numbers, and you get the displacement is going to be equal to 31.9 meters. So it rises up 31.9 meters above where we started. Part B says, how long does it take to reach its highest point? So we know the initial velocity, we know the final velocity, we know the displacement and the acceleration. So using all of that information, we go ahead and figure out which kinematic equation we're going to use. It's probably going to be the easiest one right here to figure out the time. So final velocity is going to be 0. The initial velocity is going to be 25, and then the acceleration is negative 9.8. So 0 minus 25 divided by negative 9.8, and that's going to give us a time is going to be 2.55 seconds. Part C says, how long does it take for the ball to hit the ground after it reaches its highest point? All right, so again, we're looking for time, but this time we're starting at the top and coming down to the bottom. Now we know an object that moves in the air, as it goes up, it loses its speed, but as it comes back down, it gains its speed back. So the velocity of the object at the end when it comes back down is going to be negative 25 meters per second. All right, so we got the final velocity of negative 25 meters per second. The initial velocity is 0 because we're starting at the top coming down, and the acceleration is going to be equal to the acceleration due to gravity, and we know the displacement is going to be 31.9. It's going to be negative 30.1 because we're coming from the top down, so we have a negative displacement. All right, using our kinematic equations, we're going to go ahead and plug in our, for this equation right here to find the time, the initial velocity is going to be 0, the final velocity is going to be 25, and then we divide by the acceleration, which is negative 9.8, and look at that, it's going to be 2.55 seconds, which was the same amount of time it took to go up to the top. So as it loses speed going up, it takes the same amount of time as it to gain that speed in coming back down. Next problem, part D, it says, what is the velocity when it returns to the level from which it was started? Now, we already said that the velocity was 25, but I actually want to show why this is the case. So we got the velocity, when we got the initial velocity, acceleration, and displacement. The initial velocity is going to be 25, the acceleration is going to be negative 9.8, displacement is going to be 0, which is kind of interesting if you think about it. As the object goes up and then comes back down, the total displacement is going to be 0. Now, you'll notice that we don't include time in here. The reason is because we had to use that final velocity to come back down in order to figure out what that time was. So without using time, let's figure out which kinematic equation we're going to use. We're going to use final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. We go ahead and solve for our final velocity, so we square root both sides, and then we get a plus or minus this value right here. We get plus or minus 25 meters per second. Now you'll notice we get the negative 25 meters per second squared, or I'm sorry, meters per second here, because the positive value is actually when it was going upward. So there are two places where we have a displacement of 0, where it started at the beginning and where it ended at the end. So at the beginning we have our positive 25 meters per second. So we're looking specifically at the end where it's going to be negative 25 meters per second. All right, so a few definitions, just kind of review what we've gone over. The average velocity is the total change in total change in position, which is displacement, divided by time. The average acceleration is the total change in velocity divided by time. And then some kinematic equations for constant acceleration are these right here that we've been through for this entire PowerPoint. All right, just to review about the derivative of a position versus time gives me velocity versus time. Derivative of velocity versus time gives me acceleration versus time. Likewise, the integral, the area of an acceleration versus time will give me velocity, a change in velocity. But then the integral of a velocity versus time will give me the change in position. So you can see how the derivative takes you forward and then the integral takes you back. This question says a cart traveling in a straight line in the negative x direction begins to slow down. The cart has a what? It's going to have a negative velocity and a positive acceleration, because if it's moving in the negative direction, then that means it has a negative velocity. But if it's slowing down, that means the acceleration has to be in the opposite direction, which makes it positive. This one says a block moves across a floor with a constant acceleration. So what's the answer here? So we know that the block's velocity changes by equal amounts in equal times, because with a constant acceleration is a total change in velocity over time, but changing velocity, constant acceleration is a constant change in velocity. So the velocity changes by equal amounts in equal time. It can't be the displacement changes in equal amounts, because as it slows down or as it speeds up, then every second that passes by it's going faster and faster or slower and slower, so it doesn't have the same position or same displacement for every time frame. The block moves at equal distances at equal time, so obviously not there. And that's the only difference here, is that we say distance rather than displacement. B says the block speed decreases by equal amounts in equal times. The reason why we don't say that is because constant acceleration refers to velocity. So the same thing here. The speed, where we have to talk about the direction as well. So acceleration talks about direction, so we have to include the velocity with the direction. This one says when an object is released from rest and falls in the absence of friction, which of the following is true concerning its motion? All right, so we know that the speed of the object falling is going to be proportional to the time. The weight of the object actually doesn't matter. The mass of the object doesn't matter, because gravity, the gravity of the Earth pulling on an object will actually change according to its mass. So the more mass an object has, Earth actually pulls with more force of gravity. So we get a constant acceleration either way. So the weight and the mass don't matter. It's inversely proportional to a surface area. That's not true, because the surface area has nothing to do with an object that's falling, as long as there's no air resistance. And then the speed of the falling object is proportional to the height. It's actually going proportional to the height squared. So there's actually going to be a square root in there, the speed and the height. So the speed squared would be proportional to the height. So that's why that one's incorrect. Ball thrown straight up reaches a maximum height before falling back to the thrower. As the ball is rising, which one is true? The velocity points upward and the acceleration points downward. First of all, an object that's in the air is going to have a constant negative acceleration, a downward acceleration. But because it was thrown upward, that means the velocity is going to be upward. So while it's going up, as it's rising, we have an upward velocity and a downward acceleration. Last question here, it says two balls are dropped from top of a tall building. Ball A is dropped first and ball B is dropped 1 second later. Ignoring air resistance, the two balls fall toward the ground. The distance between them, what? The distance between them is actually going to increase because by the time the second ball is dropped, the first ball is already moving. So if it's already moving, then it already has a speed, and it's going to be the average velocity of A, or the ball A as it's falling is going to be going faster all the time after B is dropped. So therefore it's going to cover more distance at an increasing time. So the distance between them is going to increase.